Hello again everyone. Today we're going to look at chapter 19.5, Spectra. This follows on obviously from 19.4 when we looked at energy levels in atoms, the idea that electrons were able to move from different energy levels from the ground state upwards, and on their way down again they would emit photons of light. So as part of today's lesson we need to look at different atoms that give off distinctive spectral lines, so different colours. And we can use that to identify what the elements are in a laboratory, and we can then translate that into what is going on in the distant space. So looking within stars. There's three different types of spectra, and that's emission line spectra, continuous spectra, and absorption line spectra. So we need to look at the difference between them. Some are done on Earth, others are done from looking into space, from the light that comes from stars. I mentioned in the last video about when you were practicing a chemistry lesson and you put a metal into a Bunsen flame and it gave off light. So that's what scientists would do, and then they compare that to what's inside stars by the colours or the very specific frequencies of light that are given off. So whilst on the previous chapter 19.4 you might have looked at maybe one or two frequencies, quite often there are maybe 5 or 6 or 7 or more different frequencies of light, and those light frequencies together give a fingerprint of one atom. So if you look in your book on chapter 19.5, figure 2, you will see hydrogen, helium and pictures of mercury. So if we look at hydrogen, you can see there's a red bit of light, blue and 2 purple-violet colours, and together that fingerprint of those 4 specific frequencies of light tell us that there's hydrogen around. Helium, a few more colours, and mercury, even more colours again. And each band of light is at a particular frequency, and together that's the fingerprint for the element. So then we know what is being emitted inside different stars. But let's look at the 3 different line spectras in more detail. If we just look at your specification points for today, so you'll be able to see C, D and E. So emission spectral lines from hot gases in terms of emission of photons and transition of electrons between discrete energy levels. So the equations which we started looking at last time, but more so today, different atoms have different spectral lines which can be used to identify elements within stars. So let's just take a look down the left-hand side first of all. So spectroscopy, so that's what this topic is really. So different elements have different spectral lines, and I've mentioned that it's a fingerprint already. And we can use this information to then identify the different elements that are found in different distant stars. So emission line spectra. Each element produces a unique emission line spectrum because of its unique set of energy levels. And this is what's observed in a laboratory from heating gases. So that's the Bunsen burner idea. So what we've got is the hot gas. We can then put it through some kind of prism to separate the lines, just like you would when you look at a rainbow. And then we can view what it looks like when those lines have spread out. So the one with the black background, that's the emission line spectrum. And that's what we meant when we looked at figure 2 in your book. So these lines here all represent a particular element. There's also something called continuous spectra. So this is what we have again on Earth. So if we have a light, we have a prism, we look at it, we see every single colour of visible light of the electromagnetic spectrum. All wavelengths from red through to violet. And the final one is the absorption line spectra. And that's got a series of black lines within a continuous spectrum. And the picture I've chosen here where we've got a red light here, we've got a black light or line just there. Likewise with the orange and the yellow and the green, and as we go down to the blue. So it's almost an inverted image of the two. But this is what we see from stars. So absorption line spectra, a series of dark spectral lines against the background of a continuous spectrum, formed when light from a source that produces a continual spectrum passes through a cooler gas, and that is inside the outer layers of our star. So as photons pass through gas, some of them are absorbed by gas atoms. This raises the electrons into a higher energy level. So only photons with energy equal to the difference in energy levels are absorbed. So if you remember back to last lesson, we had those lines that we said that had to be exact. Therefore, only specific wavelengths are absorbed, and that gives off the dark lines. And then once we know the line spectrum for a particular element, we can then compare it to that in a star. So we've got like the middle bit of the sun just here. Around the outside, you've got a slightly cooler gas, and that's where the absorption happens. And then the light gets spread out, and then what we see is the bulk of the spectrum, so that continuous spectrum. But then, if we look really carefully on Earth, we don't actually see all colours of light. If we zoom in on our sun, we might think we get all the colours, but this actually is a picture of all of the absorption lines that we would see. Put in another way, so this again would be a star. So in the middle we've got the hot, dense interior, and then the photosphere around the outside that's slightly cooler. So the light is trying to leave, and as it passes through this part, the light gets absorbed, and the light is at specific frequencies. So the light of specific frequencies doesn't make it to Earth, and that's what gives us our dark lines. And of course, feel free to pause the video and read that little bit of information there as well. So I've got a picture of our sun just here. We've got the hotter region and then the cooler region. So as photons pass through the gas, some are absorbed by the gas atoms, and that raises the electrons up to a higher energy level, and so exciting the atoms. Only photons with energy exactly equal to the difference between the different energy levels get absorbed. So this means that only specific wavelengths are absorbed, and that's what creates dark lines in the spectrum. I've put some notes in red of pretty much what I've just said for you to read, and obviously pause the video if you need to. But as the photons pass through, the electrons that absorb the energy and move up to a different transition level that's exact, and then those electrons that are there do move down again. But the reason that we get the black line is because this light that's coming straight through is going straight to Earth. But as soon as you absorb the energy and it falls back down, this light gets scattered in all different directions. So we'll get a little bit of the light from the sun coming to us, but because the bulk of the light is passing straight through and coming to us, and then the intensity of just one tiny bit of the light that's on the way to us, we then see that as just a black line, because the bulk of that light has been absorbed and scattered in different directions. We've now come to the end of chapter 19.5, so it's well worth having a go at the summary questions And as ever, any questions that you have, please do get back in contact with me.